everybody's in. So, oh, there's Bree. I might just about do it. Okay. All right. So, okay. So what we did on Thursday was talk about all kinds of things. First, we talked about local maxes and local mins. We're going to continue that today. So if you have any problems on the homework, I'd like to see that. And then we're going to add a little more onto it in terms of something I sort of talked about at the end of the session on Thursday, but we'll keep moving with it. This whole section is kind of just expanding a little bit at a time as we go. So has anybody, let me get my screen shared, so if anybody's got a question, look and see if you've got a question, and I'll get my screen shared, and then you can call the problem out to me, and so forth and so on. Come on, show my thing. Okay, all right, there's my big wave. Let's get back to my screen. Let's go down this way. Okay, so so the homework had to do with the local maxes and local mins, and it was just a little bit added on to what we did with the increasing and decreasing. And by the way, on the increasing and decreasing and critical numbers and so forth, when you scan something to me, Thursday night I had a major breakthrough, which was I can now upload your homework, download it into my my iPad. I can grade it on the iPad, red ink and all, and then send it back to you graded. So some of you have already gotten one of those back, because I graded a couple of the ones that were due, the one that was due today. Michelle, I think I graded yours. Did you get it by any chance?
I just checked my email today, but I can check it right now and see.
Well, it's all right. It doesn't matter. I think I only graded 2. One of them was Michelle's, and one of them was Anai's. Anai, I graded yours too, I think. Did
yeah,
you?
I got it.
Okay, good. All right, great. So it's back there. It's graded. It's marked. I felt like I had made a major accomplishment Thursday night, and then all that Zoom stuff came Friday. I'm like, man, every time I get on top of the curve here, somebody knocks me down to the bottom and makes me learn something new. But we'll figure after I retire, I'm going to turn this into money somehow. I'm not sure how, but we'll see. All right. Does anybody have any questions from the homework? I'm going to do some more examples, so that'll help, I think. But does anybody have any questions from the homework?
Can you do number 1?
Okay, read it. Oh, the other thing I want to tell you, wait, hang on a sec. Was that Haley? Haley, yeah. You can read the problem to me, but before you do that, let me say that when you send your homework to me, it goes into a big file with all my other classes called assignments, and I need you to head it like this for me. I'd like for you to put your first name on it. Yours will automatically go into a Math 70 file. So all I really need is your first name. And then when you rename it on your, on your scanner, which if you can rename it on the scanner by just tapping on that string of digits, and it'll let you rename it. So put your first name and just put quiz, and put the due date on it. Like today, the one due today would have been whatever it is, 4/6. And then I'll know which quiz it is, and I'll be able to open things easily. Before I figured out how to grade it all and everything, y'all were just submitting it to me as a scan, and it had like 15 digits on it, and it was a mess. I will also try, if I can find the time, to show you what you did wrong on your test. I've got them all still. Now I can upload them. I can mark them and tell you what I counted off for things, and at least put a grade on it. I told you I'd put the key online too, but I'll also try to show you what you did wrong. And that might take until the weekend. I'm under the impression that Friday, since Easter really hasn't gone away, it's just kind of gone away in a different way, that we are off for Good Friday. Because, well, y'all are off anyway. Oh, man, you don't get anything from that. Oh, well, anyway, never mind. My other classes meet on Friday, so they're going to be happy. But you might want to check with your other professors. Good Friday was listed as a holiday during the semester, so check with anybody else that you're doing anything online with and see if they're see if it's still a holiday. When I checked with the registrar's office, I didn't hear back really from them, but I had a couple of people said, yeah, it's a holiday. So that's fine with me. Okay, so Haley, you got a question. Tell me what you got.
It says find all relative extrema of the function. So
Okay.
it's f of x equals negative 2x squared plus 4x plus 3.
2x squared plus 4x plus 3.
Yes.
Okay, so that's my f of x. So negative 2x squared, that was lousy. Let me write it again. So the function is 2x squared plus 4x, there we go, plus 3. And it says find all relative extrema. Guys, relative extrema is what I refer to as local extrema. Same thing. And when they say the word extrema, remember that they're including local maxes and mins. So that's a way for them to ask you both of them. Maxes and mins. Okay, so let's do this one. The steps are the same as finding critical numbers and increasing and decreasing because you need all that to tell this. So f prime of x here is going to be equal to minus 4x plus 4. So take the derivative, be careful with the derivative. You miss the derivative, you miss everything after it. So you gotta be really careful with the derivative. Critical numbers are where this is equal to 0. A couple people are messing up on equations like this. Bring that 4x over to the other side. And even if it was a minus 4x and you left the minus 4x and took the 4 over, in order to find x, you divide by minus 4. Not just by 4, but by minus 4. So that says x is the critical number in this case. I make a line. I put the critical number on it. I test the derivative. That's where you test this to put pluses and minuses. So if I plug in 2, minus 4 times 2 is minus 8 plus 4 is minus whatever. I don't care. I just know it's minus. If I plug in 0, minus 4 times 0 plus 4 would be 4. So over on the left of 1, it's positive. I'll move something out of the way here, guys. That x equal 1 is the critical number. I'll move it out of the way of my line. Just a second. So this meant that x equal 1 was the critical number. Okay. So that means it's decreasing here. It's increasing there. Now, listen carefully about how I want you to state these things. If it's increasing, that means it's going up. So it's convenient for me to kind of put an up arrow there. If it's decreasing, it's going down. That picture right there tells you that there's going to be a peak at 1. And that's something called the first derivative test if you were looking at your book. So what we've got is we have a local max at x equal 1. And what we say is it is f of 1. So you got to find the y value that goes with it, because that's actually what the maximum is. Where it occurs is the x value. So the local max is at x equal 1 is f of 1. I go to the original function always to find points. So when I plug in here, I'll get minus 2 times 1 squared. Minus 2 is not squared, it's just the 1. So that's minus 2 plus 4 is 2 plus 3 is 5. Okay. There is no local min because there's nowhere where it goes down and then up. Okay. You only have up and then down. And this is what we're working towards, guys. So I'm going to add a little onto the problem just for the sake of looking at it here. What you will know here is this, that if you wanted to graph something that looked like this, you've got a point to hang on. You've got 1, 5 right there. And you might want to look at the original function, maybe to just get one more point. The y-intercept's easy, because if you let x equal 0, y will be 3. So I got the point. Let's just say this is the point 0, 3 right here. And what you know is that it's going to increase through that point till it gets to this local max, and then it'll go down. There's nothing to stop it going down. So you see there's no local min. And by the way, and this is what I'm going to talk about today, and what I touched on a little bit on Thursday, was not only is this a local max, it's actually an absolute max. Because if you look at what you've got there, you will see that that's not only locally high, it's absolutely high over the whole picture. Now, one other comment. In pre-calc, you might have been trained to look at this thing and say, oh, it's a parabola. It turns down because of the negative on this thing. It's a quadratic, turns down. You see, that's exactly what we got. And a calculus is a nice way to find the vertex. There's a formula for the vertex. Somebody asked me about this. It might have been you, Haley, about the formula for the vertex is minus b over 2a. You don't need that anymore. You don't need to store that formula in your head anymore. You're going to come out on a parabola, at least, with actually the locally high point or the locally low point, which is the vertex. Okay, does that answer that, Haley?
So
what?
It'll be increasing from negative infinity to 1.
Yeah, if I ask you to put this in interval notation, it's increasing from negative infinity to 1. It's decreasing from 1 to infinity. And I'll ask you for that just like I asked you on that little quiz. Hopefully everybody's turned it in. Probably I'm not going to look at it till noon, but if you hadn't turned it in, be sure to turn it in. These quizzes are going to be important, guys. I'm going to try to make them straightforward and do as many examples as I can for you. Your lowest test is only going to count half as much as the others. So if you got a low test grade and you did better on the second test, which a lot of people did, that low test grade will average together with these quizzes. If you got high quizzes, that's going to bring your low test grade up. So be religious about taking these quizzes, please, and have them in on time unless I just say, okay, I'll take it by noon or whatever. Okay, did that answer everything, Haley?
Yeah.
Okay, anybody else got a question?
Are we, would it be okay if we went over the quiz, or because some people haven't done it, we can't do that?
I don't know. I haven't collected them all yet, Katie, but I'll have it back to you soon. Here's what you got to be careful of on that quiz. The very first thing that's important is to take the derivative. Mm-hmm. I'll give you a hint on that derivative. It was a quadratic and you had to factor it. And that's important because you get your critical numbers from there, okay? And then once you get your critical numbers, put them on the number line, do what you always did, do the increasing, decreasing. To get points on the graph, you take those critical numbers and you go back to the original function. Now, guys, so one of those points was not very nice. And just go to your calculator, put it into the function on the calculator, make sure you enter it right and you'll get a Y value. That's how you're gonna deal with that. So Katie, does that kind of give you a general overview?
I think so. I hope I did it right, but
you handed it in and I saw it right before I opened the meeting, or the class. But I'll get it back to you pretty quickly because I want to make sure, because we're doing the same thing over and over again, just adding a little bit to it every time. Mm-hmm. Okay. Anybody else? Other questions? Anything else on the homework?
Could we go over number 5?
Okay. Number 5. Oh, shoot. Okay. Who's asking me that? Michelle.
Yeah.
Okay. All right. So, get down to here. All right, Michelle, tell me what the problem is.
It says f of x equals x to the 4th minus 12x cubed.
Okay. All right, good. So first step, take the derivative. It'll be 4x cubed minus 36x squared. I'm going to factor it. I'm going to bring out a 4 and an x squared, and that'll leave me with an x minus 9, I think. Let me check it. That'll be 4x cubed minus 36x squared. Okay, so there's the derivative. The critical numbers, whatever would make this 0, it doesn't matter if it's squared. It doesn't matter if it's raised to the 100th power. If x is 0, x to any power is going to be 0. So I only have to list it that one time. So there's a critical number, and clearly the critical number from that one is 9. Okay, Michelle, did you get the critical numbers?
Yeah.
Okay with that? Okay. All right, so let's see what we got here. There's 0 and 9. Now, here's where that square right there does make a difference, because when you start plugging in and testing here, I'm going to show this one. When you square this, I can tell you that this thing's always going to be positive, because no matter what you plug into it, if you square it, you're going to get something positive. So if we pick something bigger than 9, it makes that positive. 9 squared is clearly positive. 4 is times 4. So we've got a positive in there, which means it would be increasing there. Between 0 and 9, say at 1. 1 minus 9 will be negative. 1 squared will be positive, times 4 will be negative. So in there, it's decreasing. To the left at minus 2. Minus 2 minus 9 is going to be negative. But minus 2 squared, still positive. So negative times a positive is actually going to be negative there. That looks a little different. When you do simple problems like this, you might think, well, it always alternates. Well, it doesn't. That power makes a difference there. So if I were to write the increasing, decreasing stuff, guys, it would look like this. It's increasing from 9 to infinity, and it's decreasing. It's increasing from minus infinity to 9. If you want to, you can sort of break this at 0, because technically it's not decreasing there, and I'll tell you why in a minute. So you could write this one of 2 ways: minus infinity to 0, union 0 to 9. And I'll tell you exactly what's happening when I look at the graph in a second. So is there a local max or a local min here, guys? That's decreasing. That's decreasing. Somebody trying to get in? I'm not sure. Okay. That's decreasing. That's increasing. Where do you see this thing coming to a hill or a valley? Michelle, your question. Where do you see that happening?
At 9.
At 9. Yeah, there's a local min at 9. All right, there's a local min at 9. It is, and guys, this is the way I want it written. I'm real picky about this. It's f of 9. And if you go back to the original function and plug in 9, oh boy, 9 to the 4th minus 12 times 9 cubed. Somebody got a calculator, compute that for me while I'm fiddling around with this thing. 9 to the 4th minus 12 times 9 cubed. 9 to the 4th minus 12 times 9 cubed. That's in the original function. Anybody, Michelle, have you got a number on that?
I got negative 2,187.
Anybody else confirm that?
Yeah, I got the same thing.
Negative 2,000 what?
187.
Negative 2,187.
187.
Say it again. Anybody? I didn't hear that last question. So it didn't ask you to do this. It just asked you, well, they ask you what it was. What it's going to look like in the graph, if I think about it, and I see where it's increasing and decreasing. What's the value of the function at 0, by the way? Because that was the other critical number. It might help me. Where'd it go? What's the value of this function at 0? Right there. It wasn't a local max or a local min, but what's the value there? I plug in
0.
I'm gonna get 0. Yeah, I'm gonna get 0. So here's what I see from this. If I had asked you to graph it, which is going to be the ultimate thing we're going to do, it goes through 0, 0, and then at 9 it goes way down here to whatever, minus 2187. Here's what's happening with that. It's decreasing everywhere from 0 to 9, but we had a critical number there. What happens? Critical number, remember, is where the derivative or the slope of the function is 0. It flattens out just for a second and then keeps on going down. So if you were to draw a horizontal tangent line there, that would be a place where the derivative is 0. It's just that it kept going down instead of going back up. And then after this one, it goes up, which is what makes that a local min. Michelle, that was your original question. What kind of problem were you having on it?
I just, because I saw on the number line that it was both decreasing, and I wasn't sure if that was right.
So if it's doing something like that if it's both decreasing.
Okay.
All right.
Yeah. Thank you.
Okay.
So we're asking the book, find all relative extreme. Like, where do you stop at the answer? You just put
Well, in this,
local
look,
min
guys,
at,
I'm going further.
x equals 9, and then that's it.
Yeah, no. Here's what you do. I'm going a little further because I know where I'm headed, and I want to show you things as I go. What they're asking you, you would say the local minimum is at 9. It is f of 9. So it's at 9 and is.
Okay, I just want
Yeah,
to make sure.
that's all they're asking. That's all that they were asking. In the end, I'm going to have one long problem that tells you to do a lot of things that'll add to this eventually. Okay. And this is part of it. Getting a graph without, look at that, I had 2 easy points. That's not something you would be able to graph normally without plotting a lot of points or grabbing your calculator. Okay, anybody else got a question? Okay, let me go back. I still want to do a couple of examples here, and then I'm going to add a few things on to what I've done. And then some of these examples will be, since I think you're doing okay on the homework, this will be just a little added stuff. If I said f of x, okay, so here's where we're starting the lecture, guys. If I said f of x is x cubed and took the derivative, the critical number would be 0. To the right of 0, 3 times something squared, like 2 squared, would be positive. To the left of 0 at -1, say, -1 squared would still be positive, and times 3 is positive. That thing right there has neither a local max nor a local min. So in that one, we say there's no local or relative extrema. No local extrema. Because you have to have up, down, or down, up before that happens. So both of these are increasing. And it's what Michelle was asking about a second ago. If you look at what happens at 0, when you plug in 0 to the function, it goes through the point 0, 0. So what this one is doing is increasing until it kind of flattens out just for an instant, and then it keeps on increasing. In order to be a local max or a local min, it has to be the highest thing around. Well, that is not the highest thing around. It's got low points to the left and high points to the right. It's in the middle of the pack. It's not. There's no local extrema there. Okay, so no local extrema. So that's an example of what Michelle was asking me. Let's look at it one more. So the point of this is there may not be a local max or min at the critical point. The signs must change around the critical number to be one or the other. All right. Let's do another example. This is a messy one. And I don't know if I did this. I might have talked about this a little bit in class on Thursday, but the domain of this function, if I rewrite it, it's 2x minus 3 times the cube root of x squared. The cube root, I can have negatives or positives in the cube root, so there's nothing I need to throw away from that domain. The domain is minus infinity to infinity. There's no denominator there that's in danger of becoming 0. So my first step is to differentiate it to find the critical numbers. So when I differentiate it, I get 2. So derivative of 2x is 2. This is to the 2/3. So I'm going to bring down the 2/3. That'll be 6/3, which gives me 2. And then take away 1 from this, and I'll get x to the minus 1/3. All right, that's a little messy. You cannot find critical numbers unless you find a common denominator here. So here's where your algebra kicks in. I'm going to drop this power right here, because it's negative, into the denominator. I'm then going to find a common denominator. Well, that common denominator is x to the 1/3, because that's nothing but a 1. That one right there did not have the common denominator, so I give its numerator the common denominator. That's how I find common denominators. You need help on that. I'm going to sort of try to do office hours by appointment, so everybody's got me personally. So if you're having trouble with that, just shoot me an email, and I'll make a time for us to meet on Zoom. Okay. I can pull a 2 out of this, and if you look at this, the numerator becomes 0 at 1. So one of the critical numbers is 1. Now, there is another critical number here, guys, and this you have to sort of think about. If there's a place where the derivative is 0, that's a critical number if it was in the domain of the original function. So normally we don't pay much attention to things like that, to zeros and denominators, but if a 0 in the denominator of a derivative is 0, if the function exists there, then it is a critical number. Go back and look at my definition of critical number, you'll see that. Now I'm going to test some values here. If I put in, say, 8 over here, cube root 8 is 2, 2 minus 1 is positive, cube root 8 is 2. All of that over there is positive, easy to check. If I plug in a half, guys, you don't need to do the arithmetic on this. Do a quick check. The cube root of a positive number is positive, but the cube root of a half is going to be less than 1. So that's going to be negative. Cube root of a half will be positive. Negative over positive is going to be negative. If that scares you, picking a fraction to plug that in, put it in the calculator, or put in 0.5 to this and put it in the calculator. Because you'll still get, you'll get what you need. It's either positive or negative. I don't care about the value, I just care if it's positive or negative. If I look at over here, say -1, the cube root, let's look at this, that'll be the cube root of -1 over the cube root of -1. That's -1 minus 1, so that'll be -2. This thing right here is -2. So that'll be -4 over -1. It's positive. I don't care that it's 4, I just care it's positive. Okay. So here's what's happening in that problem. And the reason I'm showing you the graphs prematurely in a way, because the book isn't doing it yet, is that I want you to see what's happening at particular critical numbers. If I plug 0 into the original function, I'll get 0. 2x twice 0, cube root of x squared times 3 is 0. So I've got a point on here that is 0, 0. Okay? I'm going to put a point right there. If I pick something to the right of 1, let's just say I pick 8. Okay, that's a 1 there. So if I pick 8 and put it in the original function, I'll get another point. That's, so 2 times 8 minus 3 times 8 to the 2/3. And again, you want to put in the calculator, fine. That's 16 minus 3. 8 to the 2/3 is the cube root of 8 squared. So the cube root of 8 is 2 squared is 4. 16 minus 12 is 4. Okay? So, sorry, that's, it's 4. Oh, it's 4. So I've got another point here. So let me go back to where it was here. So if I plug in 8, I get 4. If I plug in, I should have plugged in 1. 1 was a lot easier to plug in. Why don't I plug in 1? That's 2 minus 3. It's -1. So because the cube root of 1 is 1 and that thing squared is 1. So you can plug that in there. So if I plug in, so if I say what's f of 1 here, just to get a point on the graph, it'll be 2 minus 3 or -1. Now let's try to put all that together. So I've got a point, I'm going to go back there. I got a point 0, 0, and I got a point 1, -1, right there. So let's talk about local maxes and local mins. This going up, going down. Tell me what happens at 0. Is it a local max or a local min, guys? Local max or local min?
Local max.
Local max. That's right. It's a local max. So we say there's a local max at x equals 0. It is f of 0 equals 0. So right there is a high point. There's a local min, notice down and up around there. There's a local min at x equal 1. And we found out that it was -1 by plugging it into the original. when you watch this video again, listen to me. When you find points, it's plugged into the original. So I think that's -1. So this point right here was 1, -1. I can sort of draw the graph now because that means it's increasing to the left of 0. So it's going up. Oh, whoa, get out of there. Okay, it's going up. It's decreasing in between 0 and 1. So when it gets to from 0 to 1, it does this. All right. And it increases over on this side. Now, there are things I need to tell you. And I'll save this for a later lecture, but I will say that derivative didn't exist at 0. What kind of places doesn't the derivative exist? What's the one place you think of about a derivative not existing? Anybody?
A horizontal asymptote.
A vertical asymptote or a sharp point. The only thing that could really go here, and here would be a sharp point. And I'm going to find out later that I can draw an increasing that's kind of bowed up that way. And I can draw a decreasing that's bowed up that way. I mean, there are two kinds of increasing. It could be bowed down or it could be bowed up. Because the derivative doesn't exist there, I know it's this. But I've got another thing to do that'll help you with knowing what that really looks like. So that's what that one looks like. Okay. All right. I think I'm going to skip this next one. We'll come back to it later. Let's see. And I'm going to go on to absolute maxes and mins, and I'll come back to that one if I need to. All right, I'm going to go to another screen, guys. And let's see, what do I want? Math 70, why is that in there? Absolute maxes and mins. Okay. All right, so we talked about local maxes and mins. Absolute maxes and mins are things that are the absolute highest point or the absolute lowest point. So if I draw a picture for you here, guys, to sort of describe what I'm saying, look at I'm gonna sort of, I'll erase this in a second. But if I said, here's a graph, and I told you that it existed from here to here, and suppose that was maybe 5, 6, and this was 2 minus 3. Maybe that was -1, 4. And maybe this point right here was -2, -1. Now, what's the absolute highest point on that graph right there, guys?
5, 6.
5, 6. We say the absolute max is 6. The absolute max is 6. It occurs
Emily
at
said
5.
she was trying to join back in. She wanted me to tell you.
Who is?
Emily?
Oh, okay. Let me see. Let me check. Oh, I'm sorry. Emily, you in? I think I got her in now. Okay, now I know how this works, guys. If you leave, I have to admit you back. So, Emily, are you there now? I don't know if her mic's off or on. Can't see her. I think she's back in. Okay.
Yeah, I'm here.
Okay,
Sorry.
all right, good. I have to, when you leave, if you leave, I have to readmit you. That's a whole nother security thing. So, okay, so guys, what I was talking about here, the absolute max here is 6. It occurs at x = 5. It's like a time and a temperature. You don't, if I say to you, what's the maximum temperature? You give me the temperature, you don't give me the time. So if this were a time, 5 would be a 5, 6 would be a temperature, you give me the time. So that's the absolute max. Is there a local max in this picture?
Yeah, the -2, 1, -2, -1.
No, that's actually not, that's a local, I think you're looking at let's see, that was Stephanie. You're looking down here. Now, to be a local max or a local min, it has to be on a hill or a valley. So which one is the highest that's in its neighborhood
-1,4.
Yeah, -1,4. I call that, when I have that, that's a local max. So a local max at x equal 4, I'm sorry, x equal 1, it is, x equal -1, sorry, it is 4. So it's the highest locally, but it's clearly not the highest point on the part of the graph I want to look at. Okay, it's highest locally, but not the highest. Okay, tell me is there an absolute min here, guys? Is there absolute min in this picture?
So 2, -3.
Yeah, so we say the absolute min here is -3. The absolute min is -3. It occurs at 2. Okay, now not only is that an absolute min, it's also a local. It's a local that happens to be also the absolute. I mean, it can be the lowest in its locality, and it can be the lowest in the city, sort of like that. Now, this endpoint right here, it's neither one. It's not the highest, it's not the lowest, it's not a local. To be a local, you have to be on a hill or a valley, okay? So here's the upshot of that, and I'll go back and do some examples. When you want to know, you are guaranteed a local max, a local min, if you have a function that's continuous on a closed interval. When I say closed interval here, guys, in this one, I have stopped the function. I am looking at the function from -2 to 5. So what you need to do these problems is check your local maxes, your local mins, and also your endpoints. Because you can see that some of them can be the same thing at one time, or an endpoint can be the highest, the absolute. Endpoints can be absolutes. They can never be locals. Okay, that may be a little confusing, but let's go back and look at a couple problems. And I'll show you what theorem I'm looking at here. It says absolute maxes and minimums here. Here's my theorem. If f is continuous, in other words, there's no break or gap in the function on a closed interval. In other words, I am going to basically say I'm only interested in this function from somewhere to somewhere. I'm not interested in going up beyond that, beyond to the right or beyond to the left. Then f is guaranteed to have an absolute max and an absolute min. The absolute maxes and mins can occur either at critical numbers, left something out there, either at critical numbers or endpoints. So let me show you what we're going to do to decide what's what here. I'll give you just a second I'll run that theorem up a little ways and give you a second to look at it. It's in the book, guys, but it's what I was saying in words there. Okay. So in the example I've got here, I want to let the function be f of x is x squared minus 6x plus 2. And I'm only interested in looking at this on the interval from 0 to 5. The first thing I'm going to do is find the derivative. What is the derivative there, guys? Anybody? What's the derivative?
2x minus 6.
2x.
2x minus 6. Okay, I'm hearing a couple people say 2x minus 6. That's right. If I pull a 2 out, I see that one of the critical numbers is 3, or the only critical number is 3. That 2 is just 2, guys. Don't tell me there's a critical number of 0 there, because 2 ain't ever going to turn into 0, okay? If there was an x out there with the 2, yes, I would take the 0. But the critical number is 3. That's the only one. Now, you can do this without drawing a graph, but I want to show you how the graph plays out. It says the next thing we need to do is evaluate the critical numbers and the endpoints. So they want me to find f of 3, f of 0, and f of 5. Because the endpoints are 0 and 5, and the critical number is 3. And this is the only place these things are going to happen. So you'll be able to tell the biggest one you find in this list will be the absolute max. The lowest one you find in this list will be the absolute min. All right, let's go back up to the function right here. These are points. I'm going to plug in 3 to this function. It's going to be 3 squared minus 6 times 3 squared plus 2. And I'll get 9 minus 18 is minus 9 plus 2 is minus 7. Okay, that's 9 minus 18 is minus 9 plus 2 is minus 7. Okay, I think that's right. When I plug in 0, that's easy. That term drops out. X squared drops out. Minus 6x drops out. And I'm just left with 2. Okay, does everybody see where I'm just plugging into the original function? That's how you get points on the graph. So the last one is f of 5.
I got 57.
Question?
I got 57.
Katie, you got 57? Okay, let me, boy, that's high, isn't it? I got 5. I'm going to the middle, going to this 5 squared minus 30 plus 2. I don't think it's that much, Katie.
Oh, I did plus instead of minus. Sorry, my bad.
Okay, so it's 25 minus 30, which is minus 5 plus 2, which is minus 3. How about that? 25 minus 30 minus 5 plus 2 is minus 3. So there's that one.
Sorry about that.
That's okay. That's all right. I always check. It doesn't matter. Doesn't matter. So, okay. So if I were just to look at that list, guys, what's the absolute max here? It's in that list. What's the biggest thing you see in that list?
2.
2. Where does it occur?
0.
0. So we're going to say, and I'll write it down here and then I'll get a picture. I know that the absolute max equal 2. It occurs at x equals 0. What it is the y value. Where it occurs is the x value. Is there an absolute low point on this interval? What's the absolute lowest value in that list?
-7.
-7. So that's the absolute min. The absolute min is -7. It occurs at 3. All right, so if I were drawing this thing, guys, let's just see that's exactly what happens when you draw it. If I were drawing this thing, I would put the critical number up there, which was, I need to go back down a minute. The critical number was 3. And if I look at the derivative, right there, if I plug in something bigger, it'll be plus, like 5 minus 3 is plus. If I plug in 0, I'll get negative. It's decreasing here and increasing there. If I put all that together with my information, I'm going to plot these points first of all. I've got the point 0, 2, 0, 2. I've got the point 3 minus 7. Go up a little ways. 1, 2, 3, sort of down here. 3, way down here somewhere. 3 minus 7. And I've got the point 5 minus 3. So 5 minus 3 right there. All right, I'm gonna just screen that off for a minute. So when I draw this, it's decreasing through here until I get to 3, and then it starts to increase. But now here's the deal, guys. I said I only wanted to look at this on the interval from 0 to 5. Now, I'm sorry if you drew that in your notes. I have the magic ability with my little pen here to redo what I did. I really only want it from well, I have magic ability to look up things too. I really only want it here. And I don't want, I'm going to try to erase this without erasing all of it. Erased all of it. Okay, it looks like that. All right, so if you notice then, our highest value right here was at this endpoint. That's what we said. The absolute max was 2. Our lowest point was at 3. It was -7. And then that was the other endpoint. In other words, if they give you an interval that's closed on both sides, and it's closed because it's got brackets, guys, then you're just going to stop your graph there. And that's where you read the highest and the lowest from. Is there a local min in this problem? Is there a local min or a local max? Is there a local?
Would the local min be the 3, -7?
Yeah, well, the local min is -7. It occurs at 3. So not only is it the absolute min, it's also a local. It's not only is it the lowest dog in the city, in the neighborhood, it's the lowest dog in the whole city. Okay, and the whole city is 0 to 5.
What exactly do you mean when you say that it can be the absolute min and the local min? Like, what? How do I know?
You
Is
don't.
there an example of one that has a lower one and not?
No.
Oh.
Well, yeah. I mean, you could draw something like that, and or maybe make it go down this way. The absolute max would be here, and the absolute min would be there. Would be absolute max here, absolute min there. These are locals. Locals are always given to you by this increasing and decreasing around them, okay? But the point is that they can be local. You could identify it as a local, and then you could identify it as, it not only is it locally the lowest, it's the absolute lowest.
Okay.
Okay, does that help, Katie?
Yeah.
Okay.
So it's a local min at -7.
No, say the local min is -7, it occurs at 3. Here's the way to think about that, guys. What the local max and min is the value of the function. Where it occurs is what you have to plug in to get it.
Okay.
That's what it means, okay? So you always say the max or min is the y value. It occurs at the x value. I keep talking about time and temperature, guys, but let me show you something else here. If I looked at these things and this doesn't make much sense because you don't have negative time. If that was time and temperature, and I said, what's the maximum temperature? You'd give me a temperature, you give me a y value. And if I said, well, what time did it occur? It occurred at the x value or the t value. That's what it is. Okay, let's do one more, just looking at the graph. Suppose you graph something, you plotted the endpoints, and then you got it all graphed out. What's the absolute max in this problem? What's the absolute max in that picture right there?
3, 7.
Don't say the point. Say it like it should be. The absolute max is 7. It occurs at
3.
Okay. So absolute max right here. Absolute max is 7, occurs at 3. It occurs when you plug 3 into the function. That's how you get points on the graph. Okay, is there an absolute min here, guys? Is there an absolute min?
Yes.
What is it?
3, and it occurs at 0.
That
3.
good. You said it right. I was waiting for you to say it right. Okay, so the absolute min is,
Gotcha.
is 3. It occurs at 0. But I had to see all of the endpoints and everything to make sure. What is this thing right here? What's that one right there?
Local max?
Yes, it's a local max of 3. It occurs at -4, but it's not absolute because it's not the highest thing around.
Wait, wouldn't the min be 0, -3?
Oh, I'm sorry. That's my bad. Thank you, Emily.
That's why I was so confused.
Yeah, no. That's my bad. I
Okay.
get it wrong.
Okay,
Sometimes when I make out these notes, I'm
gotcha.
mess up. But you're right. It's
Okay,
0,
okay.
-3. Thank you.
Gotcha.
If it were 3, it would. Never mind. It'd be wrong.
Yeah, I
Anyway,
was like, I didn't know where the 0
Yeah,
was. So,
thank you.
yeah,
It's
gotcha.
0 -3. There's the origin right there. Yeah. Okay. So what I want you to do for homework, guys, is look at these problems. I think this is what I wrote on your assignment sheet. Who knows? I tried to match them up. But look at those problems. Your book is not necessarily going to ask you to do this, but see if you can draw the graphs like I've been doing. That'll help you in stuff that's to come here, guys. So see if you can draw the graphs. There's a bunch of them there, but all the book wants you to do is find all the critical numbers, test the endpoints. The highest is the absolute max. The lowest is the absolute min. But if you can draw the picture, you'll see how you name things. Okay. Does anybody have any questions at this point? I think that going forward, it's all right to click on the old invitation. I got mixed messages on that, but how many people, did most people click? I didn't even send the new invitation, so I know you got in with the old invitation. I'm not changing all that stuff I played out all the way to put on the calendar all the way to May. Okay, if May ever gets here. We'll
Yeah,
see.
I just clicked, like, I went back into Zoom, which is downloaded on my computer, and
Yep.
it remembered
Okay.
this meeting, but then it had me put in the password that you had just emailed to us.
Okay,
Yeah.
guys, I'll write down that password just in case it asks you the password for the site for this. Now, write this down now, and I'm going to erase it because this is going online, and I don't want anybody coming Zoom bombing this. We got a new word in the vocabulary here.
Is it the same one you emailed us?
Yeah, I think I did email,
Okay.
but I'll give it to you again, okay?
Okay.
All right. So if it asks you for a password, you should already be admitted to this course because I put your names in there as people that were okay to come in. So 263987. If I get motivated, maybe I'll just change all the stuff I put in. But anyway, that's what the password is going to be going forward for me, for our classes. Okay? Has everybody got it? Because I'm getting ready to 86 it. Okay? All right. All right. Anybody, last questions before I say goodbye till tomorrow? You doing okay? Is everybody feeling okay about things?
I noticed that we have another quiz on Moodle. When is that due?
You know, I need to look at it, and I'm not going to keep you right now. I'll look at it and I'll email. Okay, I'll email you on that. It's on maybe on Absolute Maxes and Absolute Misses. Katie, let me look at it. I can't pull it up at the same time without cutting on my other computer, and it takes forever to load up. I will send everybody an email and make clear what that date is. I think it's on Absolute Maxes and Absolute Mins, but I'll check and see. Okay. I don't think it'll be. I mean, if it's on Absolute Maxes and Mins, it won't be due any earlier than Wednesday. Okay. Everybody okay with that? All right. Okay. Well, I'll see you tomorrow, and have a good rest of your day. Later.
Thank you.
Bye.
Bye-bye.
Bye.